Hello. We had already discussed about the Biot-Savart's law and its application, and today in this video we'll be going further into the topic of the magnetic effect of electric current. Uh, Mostly we'll be dealing with moving charges and the magnetism that they are associated with, or the magnetic force they are associated with when they are under the influence of some external magnetic field. Now, the electrons or even any charged particle, as it moves along a certain direction, it has some amount of current associated with it, and that can produce the magnetic field by itself as well. But we wish to obtain the force that is acting on it when it is subjected to some external field. So, force on a moving charge due to an external magnetic field. Now, if we have a magnetic field which is supposedly acting along this direction, this is the magnetic field B vector, and we have a charged particle, a charge say q, which is moving along that direction, and it has a velocity v. Then the force, now it's obviously making a certain angle theta with respect to the magnetic field. The force that the charge experiences due to the external magnetic field is given by the charge q multiplied with the cross product of v with b, qv cross b. Now the cross product of v and b is obviously by uh, the product of vectors, that is vb sine theta, where theta is the angle between them. In this case, if we the velocity of the charge is obviously the direction it is headed towards. As we can see in the figure, the direction is along this line. So v cross b, if you apply the right hand thumb rule that you know of, then you will find that this force that is acting on the charge will be driving it out of the plane, which can be represented by a dot encircled. So this is the value, or uh, the force that acts on the charge q when it is subjected on the moving charge. Now the important thing is that it has to move in order that it experiences a certain force, because it is directly proportional to the velocity over there. If there is no motion, if the charge is stationary, for stationary charge the force won't act on it due to the external magnetic field. So the charge must be moving with a certain velocity first of all, and not for stationary charges, of course. Now this expression will lead us to the certain concepts related to the formation of particle accelerators that we know of. Now, before heading over to that, we would like to see how the electron behaves, or what trajectory does it take when it is subjected to some perpendicular field. In this case, in the first case, let us assume the trajectory in case of an electric field, external electric field, acting normally on a moving charge. So let's see the trajectory of a moving charge subjected to a normal electric field. Now suppose we have the charge placed, we have a plate arrangement over here first of all, and these plates, they are positive and negative plates. So we have the positive plate over here and the negative plate on this side. Is this is the x-axis and this is the y-axis. Now if we were to release a charge from one end of that tunnel, uh, the charge being q, and if it were to move along this direction with a velocity v initially, then there shouldn't have been any problems with that. But the thing is that here we'll have an electric field, a uniform electric field E, to be acting along that direction as shown. And with that electric field acting, the charge is acted upon by the electrostatic force along the same direction. We assume that the charge is positive, so it gets a repulsion along that direction, and as a result of that, it will, just like a projectile as we know of, it will be taking a parabolic path. We just need to see that if our assumption is right. Now this would have been the line of motion, but it took this path because of the disturbance that was created by the external field over there. Now initially, along the y direction, let us suppose the distance that it has traveled along the y direction is simply y, and that happens in the time t, let us say, which is the time that it takes to travel from this end to this end, which is at a distance, which is stretching at a distance x. So it travels in a given time t from this end to this end, and the distance being x between those two ends, and also at the same time, because of the force acting in the vertical direction, it is pushed through a distance y along that y direction. Now along the y direction, initially the speed that it had was 0 because there was no, it was moving with a velocity v along the x direction. We can take this as ux as well, but we'll leave it as v as we have taken it. So uy initially is 0, and then it was subjected to some force which resulted in some acceleration in it. Now if the mass of the charge is m, then we have the electrostatic force QE, which is acting along that upward direction along the y direction, resulting in an acceleration of the given mass as per the second law by Newton. So we find that the acceleration is QE divided by m. Now with that acceleration available to us, what we can obtain, we can just use this x direction. Now along the x direction, it has continued to move with that same velocity v, because there was no acceleration or negative acceleration along the x direction. So along the x direction, it has continued to move. Through a distance x in, suppose, a time t with a constant speed v. So with that speed, which is the given speed, of course, right from the very beginning, so with x and v available to us, we can just substitute the value of t as x divided by v. Now for that y direction in that time t, as it covers a distance y, we have s is equal to ut plus half at squared. So we have in this case the direction, the displacement along the y direction is simply y, and this is uy times of t plus half a that we have obtained times of t squared. Now uy is 0 as we know, so this is simply y is equal to half the value of a is qe divided by m as we know it, and that of t is over here, that is x divided by v squared. So that means we have the value to be equal to half qe divided by m v squared, all of that, and we can keep that in brackets, and this is x squared. Now y is proportional to x squared over here, which tells us that the path has to be or must be parabolic. So we know from this that for a moving charge uh, subjected to an external field will take this kind of a trajectory, and a parabola can be considered to be a part of a cyclic path if that completes itself somehow. But here it is not the case. We'll see how it completes and changes into a circular path in case of the magnetic field acting normally, which is what we are going to study in the next segment. So let's move over to that. So the trajectory of a moving charge subjected to a normal magnetic field, where we see that suppose we have an electron, not an electron but any given charge, positive charge, let's assume a positive charge for now, and it's moving with a certain velocity v along this direction, and now it is subjected to some external magnetic field which is acting normal to the surface. So we have the magnetic field acting normal to the surface that we see. It's denoted by those crossed uh, lines which indicate that the magnetic field is directed into the plane. Let me take some more of that. So this is the magnetic field which is directed into the plane, and as this charge moves, the field being directed into the plane, you can use once again the right hand thumb rule, and from that you have the formula for force, that is equal to qv cross b. So v is acting along the x direction in this case from the figure, and b is acting into the plane. V cross b, if you curl your fingers of the right hand from v towards b into the plane, then your extension of the thumb is going to be in the y direction, that is in the upward direction. So as a result of that, the magnetic field, the force due to the magnetic field initially will act along this direction that I have indicated just now. So as a result of that, the force acting in that direction to a charge, we have just seen in the previous case that when that kind of force acting in the upward direction for a charge moving horizontally, the charge takes up somewhat this kind of a trajectory where it is taking a parabolic path. Now as it reaches this point, considering the tangential case, it has now the velocity to be acting along this direction. The speed may be the same, but the velocity is obviously has changed because the direction has changed. Now with that change in velocity along that line, with b still acting continuously into the plane, v cross b, you can extend your four fingers of the right hand along that arrow that I have just drawn, then curl them into the plane, and extending your thumb of your right hand, you will know that the force now will be acting along this direction. Now, force acting along this direction, the particle moving the upward direction, that is along the y-axis right now at that instant, will further bend it along that same parabolic path, just like this. So now again it follows the same idea, and then at this point the tangential velocity is acting along this direction. The field still acts in the downward direction continuously, and from your right hand thumb rule you can use it to find that the force now acts along this direction. With that force acting along this direction, it will bend the trajectory along this line. So as you can see, by the time it comes here and its velocity is headed along that direction, it will further be bent along this path to complete the circular path, again due to the force from that magnetic field. So the trajectory that we were so much concerned about in this topic, in this discussion, is a circular one, that the charge takes up a circular trajectory as it is subjected to an external field acting normally to it. With this thing known, we can consider the mathematics of it. What does the mathematics say? Well, the mathematics says that there's a magnetic force which is acting on it, force due to the magnetic field. Let us say it is FB. In terms of magnitude considered, it is simply QVB. Remember that the field is acting into the plane while the charge is moving along the plane. That is why the sine theta is always going to end up as sine 90, which is always going to be 1. So we are left with QVB. And this has resulted the charged particle to take up a circular path, and as a result of that, we can say that this force due to the magnetic field contributes to the centripetal force. Now this charge may take up a radial distance from the center. It will have a center supposedly at O. We are considering it for now, and the radius or the radial distance being r, what we get to know is that the centripetal force experienced by it is equal to, supposedly its mass is m and it was moving with the speed v, of course, mv square divided by r. Well, that's the value of centripetal force. Who has contributed to the centripetal force? It's that force due to the magnetic field. So FB being equal to FC in this case, in terms of as far as the magnitude is concerned, what we get is QVB is equal to mv square by r, and so one of the v's can get cancelled out. So we have r to be equal to mv divided by qb. This is the value of the radius. Now the greater the speed with which the particle moves, the greater will be the radius, the less is the magnitude of the charge, the greater will be the radius. Once again, the lesser the magnitude of the magnetic field acting. This is as far as the equation is concerned as we see it right now. But again, we know that we won't be talking about the magnetic field as of now. We'll be just discussing the velocity that is there at the top. The particle may change its mass if it is extremely light particle subjected to a very high velocity. Then the relativistic case may come into picture. Now this is used to accelerate such charged particles across the particle accelerators, typically in the case of the cyclotron. The cyclotron, what it does is that it takes up any charged particle that is to be accelerated and projected or projected into a given target, so at a certain speed with a certain kinetic energy. For experimental purposes, it is subjected to this cyclic path, whereupon it accelerates. It achieves that acceleration required to strike the target uh, at the exact accurate kinetic energy, so as to produce some expected result. Now this obviously will have a certain time period associated with it. The time period is equal to the total distance traveled divided by the speed with which it does so. So 2 pi r is the distance and the speed is a v. We have the value of r with us, so we have 2 pi mv divided by qb for that r, and v for velocity or speed, the v's get cancelled out, so we have 2 pi m divided by qb, which tells us that for a given charge with a certain mass and magnitude of charge intact, we have the charge is invariant, of course, in relativistic consideration, but mass may change. So the magnetic field must be changed accordingly, so as to put that given charge uh, in that same time frame or in that same time period. From that we can obtain the frequency as well, which is equal to 1 by the time period, that is equal to qb divided by 2 pi m. So as you can see, in order to synchronize the, what kind of synchronization are we talking about? We'll be talking about it in details in cyclotron, but over here what we see is that there will be some uh, problem in synchronizing the motion of the charge when it approaches that relativistic speed, whereupon its mass changes, and so the field that is being applied, that must be changed accordingly, so that the frequency that we have obtained over here remains intact or remains constant, so as to have a smooth running of that device. Now this is more or less the case when the particle is placed like that. But what about a special condition where the particle, the field is acting along this direction, suppose, and the particle is not normal to the field, but it is moving with the velocity, just like I had started off with this diagram, that it is moving with a velocity v, making an angle theta with respect to that external field. Then what do we get? Well, in this case we can consider two components of that velocity for the given charge. One of the components is along this direction, is along the line which is perpendicular to the magnetic field. This is v sine theta, and this is v cos theta. Now the thing is that v cos theta will cause the particle to move, the component along that direction, the particle is definitely going to move along that line. But what about the v sine theta? Now with that v sine theta available, what will happen is that v sine theta, being normal to the magnetic field, will undergo this cyclic process that we have just discussed, and v cos theta will raise it along the upward direction, along that direction of the field, and that is why we'll get a combination of both and eventually end up in a helical path taken up by that electron. So it probably should have moved in a certain circular path as we might consider, but here the path will be something like this. No doubt there will be a circle for sure, but it will be moving upward simultaneously as well, and as a result we'll be getting a helical path like this. So this will be the motion or the trajectory of the charge when it is uh, at a certain angle other than the perpendicular direction. So this is the helical path taken up by the charged particle. Now the mathematics remains almost the same, but the only difference being that the uh, the time period and the frequency, they are the same. The only difference being the radius, because the radius here is dependent on v. So the radius here will be, let's say it is r primed, it is because it's different, it will be mv, and which component is acting perpendicular? The component is the sine component or the vertical component, so mv sine theta divided by qb. The frequency and the time period do not contain the v term, and that is why they won't really change in this. So this is the only difference, and since we have that motion along the field, we may consider calculating the pitch. What do we mean by the term pitch? Well, it simply means the distance that is covered in one time period along that magnetic field. Distance covered along the field by the charge in unit time period. Or just the time period. So from this we can calculate it, because we know the velocity along that direction. Velocity multiplied with time gives us the distance covered. So let us say this is let's say its value is h. So h here will be equal to, the pitch is h over here, so h is equal to v cos theta, that is the speed along that direction, multiplied with the time period. Now we know that the time period hasn't changed, the time period being 2 pi m by qb. So we have the value of h to be equal to 2 pi m v cos theta divided by qb. So that's more or less our discussion for today regarding the motion of a charge in the presence of an external field. We'll be continuing with this topic, more on this topic, on magnetic effect of electric current as well as moving charges associated with magnetism, in the upcoming videos. Till then, thank you for watching.